Okay, so this is the first kinetics example problem. We have this race car on a racetrack. The car is shown traveling through a turn, which is banked at 30 degrees. The radius of the curve is given as 1,200 feet. So part A says find the velocity, find the speed v, at which the race car will have no tendency to slip sideways on the track with no reliance on friction. And part B will find the max speed v, which the car won't slip up the track if we include friction, a coefficient of static friction of 0.9. So before we begin and draw the free body diagram, let's find our coordinate system. To do that, we need to look down from above, look down on the track. So maybe the track, there's the curve, the car's traveling through this curve. So maybe the car, will put him here in the center of the curve. So where's our coordinate system? So as always, the normal direction is pointed towards the center of curvature, and then the tangent direction is tangent to the path. We'll assume that direction. We'll assume there's the velocity vector if he's at that point in the curve. So over to the car, where's the coordinate system? So the normal direction would be pointing this way towards the center of curvature. T is actually coming out toward us, so I need a third direction. I'm going to call that direction Z, and I'm going to take it positive downward, because this coordinate system, if I cross N into T, that'll equal the Z direction, just like if I crossed I into J, that would give me the K unit vector. So it follows the right-hand rule, just like an IJK or XYZ coordinate system. So there's our coordinate system. So what does our free body diagram look like? Very simple free body diagram. I'll model the car just as a rectangle. So we have the normal force acting perpendicular to the track, and then the weight acting straight down. So again, my coordinate system. So there's the normal direction, and there's the positive Z direction. So how is the car accelerating? We'll assume constant speed, constant velocity through the curve. So that means we'll have a normal component, v squared over r. It's constant velocity. The tangential acceleration would be 0, and it's clearly not accelerating in the z direction, so that's equal to 0. So now we can sum forces. I'll start with the z direction. So since it's not accelerating in the z direction, I'll sum forces in the z direction, set that equal to 0. So mg is down, so that's positive, minus, so mg minus n cosine 30 would be the z component. So there I can solve for n in terms of m. So mg divided by cos 30. So now I can sum forces in the normal direction, which will be equal to mass times normal acceleration, which is v squared over r. So what's acting in the normal direction? Just n sine 30, just some horizontal component of n, equals mv squared over r. Substitute in substitute in mg cos 30 for n. So mg cos 30 times sine 30 equals mv squared over r. Mass on both sides cancels out. So I can solve for v. So v would just be equal to g times tangent 30 times the radius of curvature, square root of all of that. So v equals, we're in feet, so 32.2 feet per second squared, tangent 30 times r, square root, and there's the velocity. 149.3 feet per second, which converts to 101.8 miles per hour. Don't know why it turned black there. So not a very realistic number. Obviously a race car can travel through a turn much faster than this on the large speedways. So that's the answer for part A with no friction. So now let's do part B where we include friction. So the only thing that changes really is our free body diagram. We add a force on a free body diagram. So still have the normal and the mg, still have the same coordinate system here. So to keep it from sliding up the track, we'll have a friction force, which is equal to our max friction force, mu s times n, directed down the slope of the track. So the same procedure here. Start with summing forces in the z direction and set that equal to 0. So I'll have mg minus n cos 30, just like we had before, plus mu s n sine 30. And that equals 0. So here I'll factor out n. So this would give me n cosine 30 minus mu s sine 30 try that again. Equals mg. So n would be equal to mg divided by cos 30 minus mu s sine 30, where I'll leave it in terms of mg. So cos 30 mu s was given as 0.9, so I'll just simplify this in terms of mg. So n is 2.404 mg. So now I can sum forces in the normal direction. So that equal to mv squared over r. So what do we have in the normal direction? So n sine 30 plus mu s n cos 30. So the horizontal components of n and the friction force. That equals mass times acceleration, mv squared over r. So I'll substitute in, well, let me do another step, n sine 30 plus mu s cosine 30 equals mv squared over r. I can substitute in n. So I'll write it like that. So substitute in n, 2.404 mg times sine 30 plus mu s cosine 30. Once again, so the mass will cancel out. So skipping a couple of steps of algebra here, I could solve for v in the same way as I did before, and here's what we get. (345 feet per second). Whoops. Which converts to 235 miles per hour, a more realistic number.